Have you ever stopped to think about how your favorite apps can keep track of millions of users, posts, and connections without just collapsing into a giant corrupted mess? Well, the secret sauce is something called relational database design. It's the hidden architecture holding our digital lives together, and today we're going to pull back that curtain and see why getting this right is one of the most elegant and absolutely crucial challenges in all of tech. All right, so to really appreciate good design, we first have to stare into the abyss of bad design. We're going to start with a table that, on the surface, looks totally fine. But trust me, it's hiding a ticking time bomb. Okay, so here it is, our user joins group table. Super simple, right? It just tracks which user is in which group. But look closer. See Lisa, user 857? She's in two groups, so her name is in there twice. Same deal with Ralph. We're repeating information, and you might think, so what? But this little bit of repetition, it's the root of almost all evil in database design. I mean, really, what is the big deal? A little extra text, who cares? Well, this seemingly harmless habit, what we call redundancy, opens the door to some truly disastrous consequences. We call them anomalies. And this is where things get really ugly. First, you've got an update anomaly. Let's say Lisa changes her username. You now have to hunt down every single place her name appears and change it. If you miss just one, your data is now a lie. Then there's the insertion anomaly. You can't add a new user to your system until they join a group. There's literally no place to put their information. And finally, the scariest one, the deletion anomaly. If you delete the Gov group and that was the only group Millhouse was in, you could accidentally wipe Millhouse from existence in your database. Poof! Gone. Yikes. So all this chaos, the redundancy, the anomalies, it's all just a symptom of a much deeper problem. We've accidentally broken a fundamental, hidden rule in our data. To fix this mess, we have to put on our detective hats and uncover the logic that's supposed to be running the show. And the number one tool in our detective kit is the functional dependency, or FD for short. It's a really simple but incredibly powerful idea. It's just a rule that says, if you know the value of X, you will always know the value of Y. We write it with a little arrow. X determines Y. You see this stuff all around you in the real world. Think about a mailing address. If I tell you the zip code is 90210, you instantly know the city is Beverly Hills and the state is California. Every single time. That's a perfect functional dependency. Zip code determines city and state. So let's bring that detective lens back to our broken table. What's the hidden rule we violated? It's this. A user's ID, their UID, must uniquely determine their name. There should only ever be one name tied to user ID 857, and that name is Lisa. Our original design broke that fundamental truth. Okay, so we found the broken rule. Now what? Well, we need a way to test our database design, right? A formal health check or a gold standard that tells us if our structure is solid or if it's a disaster waiting to happen. And that gold standard has a name. BCNF. Boys Cod Normal Form. I know, it sounds super intimidating, but the idea behind it is just beautiful. It says this: for every single rule, every functional dependency in your table, the thing on the left side of the arrow must be a superkey. And a superkey is just a fancy way of saying it's a unique fingerprint for an entire row. BCNF demands that every fact in a row must be determined by that fingerprint, and nothing less. And this is where the penny drops. This is how we prove our design was bad. In our original table, the unique fingerprint, the superkey, was the combination of user ID times group ID. You needed both to find a specific row. But our rule was just UID determines uname. Since UID by itself is not a superkey for the whole table, it's a BCNF violation. That's the smoking gun right there. So how do we fix a BCNF violation? We perform what is essentially a clean, logical data breakup. The process is called decomposition. We're going to break this one dysfunctional table into smaller, healthier tables where every single rule is respected. And the algorithm to do this is just so elegant. It's basically 3 steps. 1, you find the rule that's breaking BCNF. For us, UID determines uname. 2, you pull that rule out and give it its own brand new table. 3, you make another table with everything that's left over, but, and this is key, you keep the UID in there so you can link everything back together. Let's see what we get. Bam! Here's our first new table, a users table. Notice anything? Each user, Lisa, Ralph, everybody, they only appear once. Now, if Lisa changes her name, we update it in one spot. Done. The update anomaly? Solved. And the second table is now purely for memberships. It just links a user ID to a group ID. No more repeating names, no more repeating Twitter handles. It's clean, it's efficient, and most importantly, both of these new tables are in BCNF. All the rules are being followed. Problem solved. So we're good, right? Well, hang on. This brings up a really crucial and kind of scary question. We broke the table up based on a specific rule. What if we had done it a different way? It turns out, not all breakups are good. A bad decomposition can permanently and silently corrupt your data forever. This is the huge difference between a lossless join and a lossy join. A lossless decomposition, which is what we just did, means you can put the pieces back together perfectly and get back exactly what you started with. A lossy decomposition is a complete disaster. It literally invents false information when you try to join the tables. I mean, just look at this nightmare. This is what happens if we split the table the wrong way. When we try to join it back together, the database has no idea which join date belongs to which of Lisa's groups. So what does it do? It just creates every possible combination. We've just manufactured garbage data that never, ever existed. And this is the wildest thing about the term loss of information. You don't actually lose rows. You gain fake ones. What you truly lose is the truth. You lose the ability to know for sure which connections were real. The good news? That BCNF decomposition algorithm we used, it is mathematically guaranteed to always be lossless. So let's just take a second and bring this all home. We started with a messy, redundant table. We put on our detective hats and found the hidden rules, the functional dependencies. We used BCNF as our official health check, and then we performed a clean, lossless breakup to fix everything. If you remember just one thing from all of this, let it be this mantra. This is the heart and soul of good relational design. Every single piece of information in a table should depend on the key, the whole key, and nothing but the key. Now, as awesome and powerful as BCNF is, it's actually just one step on a longer ladder. There are even stricter rules, like fourth normal form, designed to hunt down and eliminate even more subtle and complex kinds of redundancy. It's an entire field of study dedicated to one thing, protecting the truth in our data. So let's just quickly recap the journey. 1. Data redundancy is the enemy. It's dangerous. 2. We can find the hidden rules of our data using functional dependencies. 3. BCNF is our gold standard health check to see if our design is sound. And 4. Decomposition is the cure that fixes the problem without creating new ones. And I'll leave you with this final thought. Every single time you use an app on your phone, you are relying on a well-designed database, working silently in the background, following these exact principles. So how many of them are depending on these hidden rules right this second to keep your digital world from collapsing into total chaos? It's pretty amazing when you think about it.